Logixpro, our software, talking about memory addressing. I'll also will tell you what do you have for Friday, what we're going to do on Friday, and I will introduce tumble wheel input device. What's tumble wheel input device? And I'll introduce to you binary coded decimal function block in Logixpro, maybe plus some math instructions. All right. So let's go for it. I'll open my Logixpro. Okay. So I'll be repeating the example we have in our course, like this example. So this is a simple example. If you can see, right, you can see my screen. Are you able to see my screen? So I have one instruction, we call it normally open, and then another same instruction and two lights, L1 and L2. Okay, I will do the same. So in here, let me see what's going on in here. Okay. Alright, so let's see. I take this and here I put another one, and I'll be having two output. Alright, so in simulation, input output. Okay, I click and drag it to here. I click on the light itself, on the input itself, drag it to here. Same, I click on the number itself. Okay. So that's what they are doing. Okay, let's see what you can see here. You have an input table. So when they click input 1, this input 1, when they click on it, then you see you have here 1. So you see it is 1. The input 1 you have, it is here 1. So it's saved in a memory. So the status of it, this input table, we call it input status file, or input table, simply input table, or again input status file. So in this file you have the status of your inputs, if they are on or off, assuming they are like here discrete input. Okay. So now, and light 7, actually here for them it's light 7. So look, this exercise is better. So light 7 is on. I'm not sure if they show us the output table. Let's see if they show us the output table. Okay, here they are showing us only the input. Okay, then here it's input 8. So input 8 will be on and off as well. Let's see. That's the input 8. So input 1 8. See, input 1 8. Input 1 8. Good. So that's basically about this exercise. Only this. And the idea is just to show you, like, you have an input file on which you save the status. So let me go download, go online, alright, and download it, and I run. Okay. So if you right click, go to data table. So you see what I did? Again, I right click and go to data table. You have here the input file. So you can see it is 1. So I hope you're able to see it, right? The status of my input 10 is here, right? So now if I click off, so it is 0. So same status of my input 1. So here I'll be having input 1, maybe in different color. Also I can see the status of it. Now both are 0. So here is input data file or input status file, in which I save in this memory. I save the status of my input. So the program, they come here to the I10 or I11 and look to the status. So he will know that if my input field devices is on or off. So same for the output. So you will see in the next video. So where is the next video here? I think they talk about output status file. So you see it's exactly same code, but they show you the output status file or the output table, right? So here it's 027 and 022, which is this one here. Okay, so let's do also. So here now I'm gonna go to integer float. No, I'm gonna go to output. So I should find output. So that's the output. Okay, you can do it this way, or you can right click on it and go to the data table, or you find it from here. Okay, so now all my output are 1. So is it clear? Any question regarding it? No. Okay. So yeah, that's the exercise. I may go offline again and okay, let's see. Yeah, because now I'm offline anyway. If I wish. Okay, so that's about addressing in memory. You can look to, for example, integer and float. Like let me here, maybe here put a timer, for example, or counter. Like, so I go to this, I click on this. I don't want to put it here, I want to put somewhere else. Okay, so I take the counter, I click and drag, I put it here. Okay, and here I put an instruction, a bit instruction. Alright, maybe this instruction here. When this is on, so I'll start counting up up to some number, assuming I'm counting bottles, bottles of water, up to 5 bottles. So I want to count up to 5 bottles, assuming, and I look to what's this C55. I mean, can I put C50 for example? Okay. So what's this C55? That's what we will see in a while. So now let me go online and download the program. So I should go to the run mode. So this is something we know, and this is we already know. So now I'll be clicking on this push button. Okay. But before doing that, let me click on it and go to data table. So it opened for me something called counter. Right? That's a counter. So if it's timer, it should count as it should be go as timer, like time. Okay. So now it's a counter, and counter is normally like integer. So that's why I take an example of I'm counting numbers. So when I say to it C50, so means, so where's my data table? Okay. So when I say C50, so that means I'm addressing in, I'm putting my timer in this register. So in this case, I'm counting up, I'm not counting down. Okay, so counting up still 0. The N is on. You see, it's green, it's yellow, and here you have 1. The N indicate like your counter is in normal operation. Like let me, for example, make it this way now. Okay, I just push the push button 1 time. Then what happens? The accumulator is taking 1. Alright, so if I press it and again, so it is 2, etc. I keep pressing, and all of those are in C50 register. Okay, so you have preset value. This preset value you can yourself change it. So now I will be showing you the preset value. So I need to go in this mode, and the preset value I'll put it, for example, 5. Okay, and I'll download my program again. So go to, okay, did I download it? I downloaded it. Accumulated value is still 0, like I start from 0 again, right? And I run the system. So now go to data table, right? I care about only this one. So the done bit here is, you can understand what's done bit. Done bit, now you may ask yourself, so why is the done bit now it's 0? It is done bit. This is done bit. It is now 0. It was 1. It was now 0. So look when it will go to 1. It will go to 1 when your accumulator value reach the preset value. 3, 4, 5, then the done bit. So means you're done your counting. Maybe you need to count until 5. After 5 you need to stop your machine. So then you use it this way. So then here is another addressing memory. So the idea now is not to teach you counter or timer. It's rather to show you the input tables or the input files and output files, also counter file. You have timer file, control file, and all of them in each for example, for chapter timer, you need to be aware that we'll look at timer file again. When we take a chapter about counter or chapter about control instructions, so we will be looking at this stuff. So we'll be looking at, so means you need to be aware, like in control instruction, we save them in R. Okay, like timer, like this, etc. Counter now, what is this? So let me close then. This is the addressing memory. That's where you address things. So keep in mind that in Logixpro, maybe the addressing is different than other software or other manufacturers. It's not standardized. Maybe counter, they call it, for example, Siemens for float number, for timer, like assuming it's a time also. They don't call it T, they call it W, for example. So they name it W. So then you need to be familiar with each addressing standard for each company or each addressing convention notation, but they name it this way. So here when you look to the timer binary, like B3, it's binary, and this is a memory value. Like for example, I can go offline and have a bit here. Alright, and this bit, if I go to table, I can go to binary, like I call it B30 for example. B300 if you wish. Let me check. If I say B again, binary, so B3 0, B3 0/0. Okay, B30/0 for example. Okay, I call it this way, and I give it an output. Very nice. And this output is maybe 023. Okay, so now I'm having B like a memory, like so they give it like you can save something in the memory by this way. You don't need to have an input status, just like this. So then you go online now and test it. So now I'm running. Okay, I know that this is something you are familiar with now, but what's for this? How to change this? You go to data table here and to the binary, which is B30. Okay, I put it 1, and then you see the change here. Okay, so now what if this instruction of this memory that I want, it is not it is not binary, it's not 0 1, it is a decimal representation. I want to represent it in decimal. I can say this is, I want it to be, if you wish, not than B300, only just B30. So B30, it will take the 16 bits, run, or not run, download, then run. So now I said this is my table that I want, not the input, the binary table. This binary table, I wanted to take this 16 bit from 0 to 16. So then this is 1, I can give this is 1 as well. But in this case, the light, okay, is not gonna turning this way because this is B33. But just I'm representing it. Maybe I want here to put not digital output on off. I want to put something else, right? Like this one, for example, 06. So now I want to put here 06, for example. Okay. So how to put 06? Then I go. I'm in already in this mode. So yeah, actually just click on it and right or drag it to here. Just 06. So now what will happen now if I run my code? Let me look to the data table for my binary. So B30 is 11. So in here it's not taking it. So I can see nothing here actually. Okay, we'll see it, but look to here. If I convert it to decimal now, my number is B30 is 67. You see, you can convert it to different, but still the same addressing. So now it's taking the whole word, the 16 bits. Okay. If you want to show it on the screen and in 06, here there is a small trick which I also in your agenda for today. It's on my agenda for today. I'll be teaching it to you. So how to visualize this? This is called binary coded decimal or BCD. So there is a function to represent it. You cannot put a normal output like this. So you need to go to your offline and go to the math instruction. And here there is something called TOD. Okay. I'll put it here. This is, I will delete if I can. Okay. It's called TOD. Here I'll keep it as a memory, but as a bit. Okay. If it is on, then activate convert to BCD. So that's what means. Convert to BCD. So then it will go, and so that's your output. Now imagine in your PLC now you are connecting a what? You are connecting a 7-segment display as a field output device. Then if you want to work with this 7-segment display, you need to put a function here, function block called 2D to TOD, means conversion to BCD. Alright, and here I don't want to put, so now you understand this is B is like to save some bit in the memory, like for example, if you go to the data file of the counter, I have C50 dot done, or C50 slash done. So if I put here C50 slash done, and I return the accumulated value to 0 for now. Okay. So, and my source is, I need to tell a source to give a source. So my source is, now I will say B, that you like, B30, that's my source, which is unique. You see B30, it show it to me in decimal. Okay, if I go to my binary, which is 1 it shows it to me in decimal, because we understand decimal as a human. And in different chapter I'll talk to you about system coding, especially for mechanical students. I'll talk a bit about system coding soon, very soon. But anyway, so now my destination will be 06, will be 06. Okay, that will be my destination. So now let's run the program. Okay, so I go online and I download it and I run. So what will happen in here? Nothing. Look, so that's I12. Accumulation 1. I count one plastic bottle, 2 plastic bottle, 3 cars, 4 cars. When it is 5 cars, I said I give order. When it's 5 cars, I give order, like the done bit will be 1. We know that's how this function works. When the preset equals the accumulated value of my items, I accumulated 5 items, 5 boxes. So then this bit will be on. This bit, when it is on, it will give order for whatever I have in my B3 to show on the screen. So now, currently I have in my B30, I have 67. So I will see a 67 in here. Let's see. So now, okay, so you see 67 here on the display. So you may tell me why here I'm seeing 103, but actually I'm seeing it here 67. Let me go to the data table and to the binary that you have, which is 67, right? If you look at it in decimal, it is 67. In octal, it is 103. That's in octal. So what you see here is the octal representation of 103. Like if in another representation, like the decimal representation, so it's 43. Anyway, so this is the 103 that you see, but you can see it here in this. So basically, if you want to look at it, so this is 0, then the second one is sorry, this first one is 1. So first one is 1, second is 1, third is 1, fourth is 0, then fifth is 0, 1 1 1 1 0, then 0 0 0 0 0 0 0 0. I should do it differently, like starting from last to beginning. So then 0 1 1 0, then 0 1 1 1. Okay, that's how you should look at it. Starting from here to here. Later on, I'll be explaining it, but now because maybe some mechatronics students are wondering, they try to connect the dots. So now, okay, now, if you count with me, please, 2 to the power 0 plus 2 to the power 1 plus 2 to the power 2, how much it is? Can you help me, please? Hello? Hello?
5.
5. 2 to the power 0 is 1. 2 to the power 1 is 2. 2 to the power 2 is 4.
8 دكتور.
4,
7.
6, 7, 8. So here is 8.
مش 7.
7.
7 is 7. And then that's why you are seeing here 7. So now here is you do the same. 2 to the power 0, 2 to the power 1, 2 to the power 2 plus 0.
هول مش منكفيون 2 to the power 3 4 5.
No, because octal. So here, like, because binary coded decimal, again, is even mechatronics student, you will get the chance to refresh your memory about system codings in another chapter. But now, just in case you still remember, so this is, then if you count it with me, is 1 plus 2 to the power 1 is 2 plus 4. Here is 0, so, right? Here is 0 because 2 to the power 0 times 0 is 0, if you still remember. So then it's 6. So that's why you can see here 6. And the remaining are 0 and 0. So you see 7, 6. That's how it look like. Alright. So here they're showing it to you in octal representation. Right. Yeah, I'm not sure if I can change the representation even to something else. Anyway, so this is in binary. If I have another, maybe I change the number now. So you see the number is changing. Here is in binary. Here is in decimal. So my number is 1091. So this number is 1091. So I can see it here. Okay, you have octal representation and hexadecimal representation. Yeah. Anyway, so we need to maybe figure out why this representation here is this how. But anyway, any number you are taking at the source, at the destination, will be converted to binary coded decimal. So it will be showing here. Okay. So I want to show you. Nice. The remaining thing maybe I want to show you is before talking about Friday homework or Friday session is the tumble wheel input device. So if you wish, what tumble wheel device is, so now you will connect your PLC to a tumble wheel input. Let me show a tumble wheel input. Yeah, like this or like this. This is a better representation. So this is a tumble wheel. Like you want to connect now your input module of the PLC. You want to connect it to a tumble wheel, and you want to show that number in a display, or you want to use for arithmetic calculation, or for so that's the number you want to introduce. You want to deal with numbers, and we know as decimal human. So even you have some tumble wheel with, you can enter a float number like 12.5 or something. So those number you can deal with them in your program to do math instruction, whatever you want to do. Okay. Then if your tumble wheel input device is connected to the input interface of your PLC, also you can deal with that, like maybe offline. So now I don't want to put the counter here. I will put here I5. Okay, simply I put I5. That is nothing more. Actually, I said I5, right? I5. Okay. So now let me download my code and run it. It doesn't work this way probably because I5 it's not a bit, so this is a mistake I did. Okay, it's a mistake. So here I will take a bit, any bit. Just let's take any bit, assuming that's I want to take this. Alright, and here in my source I will put I5. Good. Then now let's run the program. Okay, I6 is on. So see, I have one here, just I'm visualizing it in the source. So this one. If you have two, that's two. You see, this is the light of two. All of those are connected by default. Just what you do, you will buy an input module and interface corresponds to this tumble wheel, and you connect it to the tumble wheel device. Also, you need a special output module, because we told you before that the input and output modules can be modular, and you just slot, you take your slot and you plug into the chassis rack. And so if you want to use 7-segment display or tumble wheel input or 7-segment display output, you need to buy for them some special input or output module interface. So then you can directly connect them. Okay, so here in the simulation, you will assume that they bought it for you, and that's why you are able to use the tumble wheel or 7-segment display. Okay. So now, here, what's the problem here? When I put 13, show me 19. So there is an instruction here called from BCD. So because here it's you take it as binary coded decimal, so you put from BCD. Okay? So that's the instruction I was looking for. So now your source is I5. Here you put your source is I5. Okay. And your destination could be any integer if you want. Your destination could be any integer. And you know the integer, right? So like if you go to your data file, integer or n7. So I choose n70 as my integer. Okay. So by doing that, That's everything I need. So then here to visualize it, so now FRD is to read the temp wheel input, and TOD is to visualize your integer into a 7-segment display. So again, FRD is to read a temp wheel input, and TOD is to visualize on a 7-segment display. Well, this example appears to be like simple things, or why do I need it? Like I want the I want to, okay, let me switch it to maybe switch like this. So it appears to be a simple example why I want to have input and visualize it. Of course the problem should be different, should be like maybe you have an input, you want to treat, use it, something, and later visualize something else. Here just I'm showing you the concept. Okay, alright, so that's it. I mean, just the function that I forgot, FRD. So look what happens, right? If you wish, I'm closing I6, or let me keep it open. So I5, it is 104. Here is the trick. The trick is like here is what your input is. What your input as a human, we put input in decimal, so it's a decimal. But your input field device is converted it to binary coded decimal. What it means, converted it to binary coded decimal, it means it takes the first number and convert it into the first 4 octet, second number the second 4, third number 1, so he converted to 4, and the last one the last 4. That's what we mean binary coded decimal. But we don't want to focus on this now. System encoding, will explain it in different chapter. Now my point only how to use a temp wheel input device, the one I showed to you visually in the photo. So that's your PLC, and assuming, well, that's your input device and it's connected to temp wheel. In this case, assuming temp wheel, it has 4 numbers. This is a special input module to read the temp wheel. So you have a special input module that you can buy. It reads the temp wheel. It will convert it to that how 001. It depends on what you are giving. So to read the 104, you use the function from BCD, because the temp wheel module convert your decimal to BCD. That's what you need to understand. It convert your decimal to BCD. That's why from BCD to integer. So you put your destination in integer and you use it in your program in case you want to use it in your program. So you see the 104 or the 144. See? So you take and you use it. So that's the block that I forgot to show you. It's in the same place in the math instruction bit. In the math instructions, you go to the math instruction, from the same place where you find TOD, you find FRD. Now, assuming I want to visualize, it's another problem also, and you want to visualize here. You buy a special output module interface to read binary coded decimal, and therefore, because you have a 7-segment display, as here, that's your output, and here is a temp wheel, your input, that's a temp wheel, and this is a 7-segment display in which you are connecting it to a special output module to a special input module. Assuming you want to read that integer. So then what you do, your integer, you want to read it, you put in the destination, which is 06. Here your source was I5. So from FRD, from BCD to BCD, TOD, like to BCD. Okay, to and from. F like from BCD on to BCD. So I will convert your integer to BCD, and that's why you can find it 144. So now you ask the question, so why 06 is 3 to 4? Let's put it in green. Why 06 is 3 to 4? And you can ask same question, why I5 is 3 to 4? So what gets us confused in our conversion when we did it here is, was basically, this 3 to 4, the way we entered the number. Like, look at the way you should enter the number. You should enter it from most significant bit to low significant. Anyway, you should enter it from here, according to this this website. So they start not from here. So I started. That's what I get me confused with. I started from here. Then I enter the number as 001 0001 01 01. Then 000 3 4 5 6 7, etc. So then I entered it this way. This is wrong. You should not enter it this way. Now if you enter it this way, then this is wrong, because the 0 will be the most significant bit. But actually your 0 is the low significant bit. So you started from here. Then you enter it from down, from bottom to top. So then in that case you will be having 001 001 0001 0001, then 01 01, then remaining are 0. When you convert, you will get 3 to 4. That's what it gets us confused with. Then it's a binary. You are converting it to decimal. This binary converted it to decimal here. So what you see here is the 3 to 4 is the decimal of your binary. Okay, what you are seeing is the decimal again of your binary. This is 3 to 4. You see, I5 is 3 to 4. If you put it in binary, it will give it to you in binary. 001 00, etc. And the destination, it converted your decimal to binary coded decimal, which is at the end whatever you have in here. Okay, so then that's the thing that you need to pay attention also. For example, if you have not sure or this number, so look at it, it's 851. 851 is the decimal of the BCD that you see it here. And you convert it, so you need to convert this I5, which is I5 at the end. That's how the machine understands it. The machine will understand it as 110001, it understands it as 01. But this, if you convert it to decimal, you will find it 851. If you don't trust your software, you can take the binary from here, the display, or from here, and use the machine. But if you enter it correctly, not as I did during the session, then you will find 851. Then this source from BCD, it will convert it to integer. It will convert it to integer. You choose to put it in N70. Your integer, you choose to put it in this addressing, because this addressing are saved in the PLC memory for integer. So you could save it in N74 if you wish. Then later the same integer, I use the 2BCD or maybe different integer from different where when you are programming. You say I want to convert it to binary. So you convert it to binary, call it decimal again. You convert it to binary code decimal, you get the 851. So that's the 851. 851 corresponds to 11, etc. And in here, your 7-segment display, it will take each 4 and convert them to a number. So then you return having this one. Okay, hope this clarifies. So then conclusion is we forgot to add the BCD, the FRD. So we was using only TOD. TOD we used for the display, to display the integer. FRD we use it for the temp wheel. So if the 7-segment display, use the TOD. If you have an input temp wheel input, so you use the FRD in your program. And conversion, you don't need really to be aware about or to look at for now. It's alright. Just need to understand that temp wheel we use FRD for it in our program, so we'll be having it because the destination will at the end will deal with the destination. Okay, so then we use this value, which is N70 in our calculation. So don't care about the source, because the source, if you wish, it's the binary, it's the decimal of this binary. Okay, that the machine understands, as we did in while. So you take 1, 1, 0, 0, etc. You put it in here. Make sure you enter it from bottom to up, or directly convert it here. And it is N70, it's 353. Okay, 353. I5. Sorry, I want I5. It is 851. Okay. So this is actually the computer will understand it as binary, as 1, 1, 0, 0, etc. And this is, if you want to convert it to decimal, it's 851. You can convert it to something else. You can to octal, anything. Okay. Hope it's clear. So in this session we talked about memory addressing. We saw integer, maybe we saw timer. You can, it's like, so you have float, etc. So basically you have the data file. So that's what we talked about. All of those are addressing. We saw the output, input, the binary. It's be like memory. So you save, it's not input or output, it's just you save something in a memory, so you may need it, as we saw in one of our examples using B3. You have timer, you have counter, you have integer, and you have float as a real number. So those are memory addressing. You can see them in binary, in decimal, etc. We introduce you the temp wheel and the 7-segment display and how you use them in your code. Alright, and those basically are in your math instruction. So you go to math instruction, you find them. Okay, but you can find math instruction, addition, subtraction, multiplication, so you can try them yourself, and in which you basically need to declare in your data table, you will probably declare a float when you work with math instruction, because you may need a comma or in the division or so. Okay, so you could experiment it yourself. What is for Friday session? So that's the remaining point in our session. What's for Friday? So Friday is you have on your data sheet, on your model, you have this data sheet. So I want to prepare it for Friday, and in the half of the session or at the beginning of the session you will tell me the specification of. So you go to your model, okay, that's model, and that's our course. It is called, yeah, that's our course. You go to it, and here in chapter 2 I'm putting it, you have Siemens PLC datasheet. So if you click on it, I'm giving you a Siemens PLC datasheet. So if I click, I'll find the datasheet. So I download and I will read it. Read it. You need to extract the information from it. Which information? You need to read the slides 50 to 57. So it is 7 slides. Only 7 slides from chapter 2. Go to chapter 2 and you read those 7 slides and find the specification from the attached datasheet. So those 7 slides, they talk about the specification basically. Okay, so if I go and read, I go to slide 50, maybe faster on my on here. So if I go to slide 50 to 57, that's so then I need to extract all of those from the datasheet. Okay, and you tell me about the 270 57. Okay, those 7 slides. What is the resolution, or how much is the resolution for this for this PLC that we have it here? Okay, Siemens PLC. So that will be your duty for Friday. So you will be coming prepared Friday morning. So we'll discuss it at the beginning, and the second half, or when we're done, I will be doing exercises at the first time. So I'll give you exercise, give you some times to work on. This YouTube will be helpful. It's 8-minute YouTube, and not recorded by me, but it's online. So you can look at it. He's talking about the Siemens PLC. This maybe the same or very close to the one you have in your datasheet. Alright, here is chapter 2. If you want to watch it yourself, I was explaining chapter 2, but it's for your own reading, for general information about the PLC hardware component, including the specification from slide 50 to 57. It's up to you. And here is adds on. Also, I did myself. For you, it's also part of your general culture about PLC, if you want. And this add-ons, of course, is related to the chapter itself. Okay, that's it for today.